All right, thank you. This is joint work with my former student, Xiao Wang, who's now a postdoc at BU and MIT before taking a faculty job at Northwestern, and with Vlad Kolesnikov, who's now a faculty member at Georgia Tech. As I was preparing the talk, I was a little bit worried I wasn't going to be able to get through everything in time, even though I try my best to speak quickly. So I want to just give an overview so that way people who can get the main result of the talk, and then they can check their email or whatever else they want to do. So basically, the talk is about constructing an efficient, non-interactive zero-knowledge proof system that's based on symmetric key primitives alone. So based on hash functions and block ciphers. It builds on prior work that I'll talk about in a few slides. Primarily for those who are familiar, it's built on a series of works called ZKBoo and ZKB++. Because the non-interactive zero-knowledge proof system, the NIZK that we build is based on symmetric key primitives only, it has, or we can conjecture that it has post-quantum security. There's nothing like factoring or discrete log or anything else for which we know efficient quantum algorithms that could be used to attack our proof system. And our aim in developing this proof system was really to come up with one that, to the extent possible, would minimize communication. We were aiming really to get as short proofs as possible while still having very efficient computation. We have linear communication that is linear in the circuit size. I'll talk more about that in a few slides. But the constants that we get are excellent. And also, as I'll show, our work is better than prior work, in particular better than ZKBoo and ZKB++ for all circuits. It's better than some other work only in a particular range of circuits. But as we'll show also, that range of circuits is also interesting from a cryptographic perspective. Once you have a non-interactive zero-knowledge proof system that with plausible post-quantum security, it's very natural and actually kind of well known how to apply that to then get constructions of post-quantum signatures. I'll talk a little bit about what we get when we do that in our case, when we do that for our proof system. And what's interesting here is that we get something that's actually quite good, has quite good performance. In particular, it has shorter signatures than what's known, at least for certain class of hash-based signatures. And we can also extend this work to get constructions of post-quantum group and ring signatures, which are also fairly efficient. So with that in mind, let me back up and give a little bit of the background. I'm sure many of the people in the audience know this already, but I'll just review quickly the notion of zero-knowledge proofs. So zero-knowledge proof consists of a prover here on the left and a verifier here on the right. They share a circuit. We'll be thinking of Boolean circuits here, denoted by C. And the prover additionally has an input, a witness W, on which the circuit evaluates to 1. And the prover wants to convince the verifier that the circuit is satisfiable, namely that there exists an input for which the circuit evaluates to 1. So we'll have a standard kind of a proof structure here. Here I just indicate a 3-round type of proof. It could be more rounds in general, after which the verifier decides whether to accept or reject. And we're going to require basically two properties. One is protection against a cheating prover. This is called soundness, namely that if a malicious prover P can make the verifier accept, then with overwhelming probability, there exists a witness for which the circuit evaluates to 1. And in particular, we'll also want something stronger, namely that we can extract from P a witness that the circuit evaluates to 1. And we'll also be looking for a slightly weak notion of zero knowledge called honest verifier zero knowledge, which says that the transcript of an honest execution of the protocol can be simulated without knowledge of W. So this means that basically an interaction with an honest verifier doesn't reveal anything about the witness. A non-interactive zero-knowledge proof is where you compress this interaction to just a single message sent from the prover to the verifier. We have soundness as before, zero knowledge as well. Here you can notice there's no difference really between honest verifier zero knowledge and general zero knowledge because the verifier isn't really doing anything other than verifying the proof. And of course, you know, this is impossible to achieve in the plain model. Classically, people achieve this by assuming a common reference string, but it's also possible to achieve this in the random oracle model, and that's what we'll do here. And basically, we'll be applying the Fiat-Shamir transform to a public coin honest verifier zero knowledge proof. This is just a standard technique, and that's why it suffices for us to consider the honest verifier case. Now, if you look at non-interactive zero-knowledge proofs for all circuits or for the class NP, historically speaking, right, the work on this goes back at least 25 years, and historically speaking, these proofs were relatively inefficient. Over the past 5-6 years or so, we've seen a number of improvements that have dramatically improved the efficiency of these proofs. Many in the room may be familiar actually with the notion of snarks, which are sublinear length proofs. These are proofs where the non-interactive proofs where the proof is actually sublinear in the size of the circuit, and they also have sublinear time verification. Now that sounds great, especially where we're trying to minimize communication. There are some drawbacks that come with snarks, however. One is that for the most part, they have poor prover efficiency. So verifier time is very good, but prover efficiency is not as good. Many of them require some form of trusted setup. And maybe most relevant here is that most of the snarks that have been constructed in the literature are not quantum secure. There are a couple of recent exceptions, including one I think you'll hear about later in the session. But at least at the time of this submission, I believe it was the case, there were no published solutions of quantum secure snarks. So as I said earlier, our NIZK proofs are not sublinear, so we're not competing with snarks from that point of view, but we are getting the post-quantum security. Now, our construction of zero-knowledge proofs relies on secure computation as a building block. There has been some prior work also on constructing NIZK proofs from secure computation. I'll go through this kind of quickly. You can see the paper for more details. There was an early line of work on building interactive zero-knowledge proofs from secure computation. Those proofs are not amenable to the Fiat-Shamir transform because they're not public coin. They also require public key assumptions, which kind of ruins the post-quantum security to some extent, and also the efficiency. Another line of work, and the ZKBoo and ZKB++ line in particular, relies on a very nice approach called MPC-in-the-head that was introduced by Ishai et al. In 2007. And you can instantiate this approach using only symmetric key primitives. I'll explain this in a couple of slides. And as I said earlier, there have been a couple of efficient instantiations of this approach, including ZKBoo and ZKB++. Also another one called Ligero, that I'll compare to later in the slide. It deviates a little bit, I would say, from the way that ZKBoo and ZKB++ were constructed, and so we don't directly follow their approach. So we show in this paper what I would call a new approach, really, for instantiating the MPC-in-the-head paradigm that has not been considered before. And in particular, what we looked at was instantiating this paradigm using secure computation protocols designed in the preprocessing model. So this is a model where you assume a trusted dealer who can initialize all the parties with some correlated state that they can then use during the online phase of the secure computation protocol. It turns out that by doing so, we can design a very communication-efficient protocol. And in particular, it turns out to make large n, where n is going to be the number of parties in the protocol, it turns out to make those protocols competitive, leading to better soundness per execution and therefore better efficiency overall. We also optimize the efficiency of the approach, again, with the aim of minimizing communication. And then, like I said, we show applications to constructing various forms of post-quantum signatures. So let me just go over the MPC-in-the-head approach at a kind of a high level to give you the main intuition of what we're doing. So the approach is, again, we have the prover and verifier, where the prover holds a witness and the verifier holds a circuit. And what's going to happen is that the prover is going to simulate in her head an execution of a multi-party protocol that's going to be evaluating this Boolean circuit C. And the way she does that is first by taking the witness W that she knows and secret sharing it among all the parties in the protocol, and then exactly simulating the protocol and thereby getting a transcript of that protocol execution. What she'll then do is commit to the views of each party in that execution and send that sequence of commitments over to the verifier. The verifier can then challenge some number of those parties, and the prover will open up the commitments to those parties' views. At this point, the verifier makes a determination whether to accept or not by looking, first of all, whether the views that were opened are consistent with a correct execution of the protocol with output 1, right, indicating that the evaluation of the circuit on some input resulted in output 1, and also that the views of these parties are consistent with each other, right? So if one party claims to have sent a message to another, the other party should have received it. Now, what's interesting here is that the MPC-in-the-head approach for constructing zero-knowledge protocols, the secure computation protocol that's relied on, semi-honest security is enough, which is in part why this approach can be so efficient. And privacy against T-corrupted parties implies zero knowledge in the resulting zero-knowledge proof system if up to T parties are corrupted, right? Because if the verifier is only seeing the views of T parties and it's a T-private protocol, then nothing is being revealed about the witness. As for soundness, it's hard to say much in general. It may depend on the specific protocol, but what you can say is that if the prover is cheating, then they have to cheat at least on the view of some pair of parties. And that means the verifier will catch the prover if at least those two parties on which the prover cheated are among the open parties. And so you can derive that the optimal probability of catching of cheating is 2 over n if you set the privacy parameter t to optimal. And the main thing to take away from that is that the larger n, the larger the number of parties in the protocol the prover is simulating, the better soundness is you're going to obtain from the proof system per repetition. As far as concrete efficiency goes, so I want to point out that even though secure computation in general requires public key primitives, you can actually avoid public key primitives entirely by using OT channels between the parties. This was something already observed in the original paper on the MPC-in-the-head. I won't go into why that's the case, but in general, you can actually use any T-party functionality because when the verifier opens T-parties, it can then check consistency of that functionality among those T-parties. This approach was optimized and implemented in the line of work ZKBoo and ZKB++. It turns out they found that empirically the best trade-off they obtained was actually setting n quite low. They set it to n equals 3, and then did a high number of repetitions in order to get good soundness for the resulting zero-knowledge protocol. So in our work, as I said, we're going to look at using the MPC-in-the-head approach, but applying it to secure computation protocols with preprocessing. So in this model, we imagine we have a trusted dealer who initializes all the parties with some correlated state, after which the parties can then run an online secure computation protocol, or the online phase of a secure computation protocol, to evaluate a circuit as before. Now, it's known that preprocessing can help a lot in terms of efficiency of protocols. What perhaps was less clear was whether MPC with preprocessing is compatible with the MPC-in-the-head paradigm. And the problem is that the prover can, of course, try to cheat by generating incorrect state during the preprocessing phase. And if the verifier is only going to be opening T parties, then that may not be enough to determine whether or not the prover has cheated in the preprocessing that they generated. Now, you can, of course, check the preprocessing by opening all the parties, but if you open all the parties, that violates zero knowledge, because then the verifier can take all the shares of the inputs the parties have and XOR them together and recover the original witness. So what we do is actually break this idea of the MPC-in-the-head paradigm into a two-stage protocol now, where in the first stage we have the prover commit to some number m of executions of the preprocessing phase, and then the verifier can request to challenge to open all but one of those. The prover will then open up all the parties' views for all but one of those executions of the preprocessing phase, and the verifier will check that they're all correct and that the preprocessing was done correctly. And then the prover can take the remaining unopened preprocessing phase and use that to simulate a protocol execution as before, and then commit to those views and have those views challenged and open just like before. Now, and of course, to allow verification, to allow the verifier to see that things are done correctly, the verifier must also have access to the state of the open parties in that protocol execution, but that can be done by selectively opening some of the party's state from the preprocessing phase that was used in running the protocol. Okay. So zero knowledge actually is fine with this approach because opening all the parties' state from the preprocessing phase reveals nothing about the input. And that's because the preprocessing that we do is input independent. And so therefore, just revealing everyone's state, they haven't even necessarily received their inputs at that point. And so even though you're opening up everyone's view at that point, it reveals nothing about the actual witness to the verifier. And then opening T parties in the second stage of the protocol is fine, just like before if we have a T private protocol. Soundness is slightly more complicated to analyze, but not by much. Basically, you can intuitively argue that the prover can cheat in the first phase, that is to come up with incorrect preprocessing that then remains and is used in the second phase, with probability at most 1 over m. That's assuming we open all but one. And then if the processing being used in the online execution is correct, then the soundness can be analyzed just like before. Now, in the paper, we show a communication-efficient MPC protocol in the preprocessing model with semi-honest security for n-1 corruptions. Our protocol has the feature that all messages are actually broadcast, which means we get soundness error 1 over n rather than 2 over n. And the efficiency, as I said, is quite good. The state of each party following the preprocessing is order of kappa bits, where kappa is a computational security parameter, except for one party who has state linear in the circuit size. And the online communication in the protocol is only 1 bit per gate per party. And remember that the way we set things up, the prover is only going to need to send one party's messages in order for the verifier to reconstruct and recheck the entire protocol. So the amortized complexity of the proof is only 1 bit per gate. And I'm not going to describe the protocol here. You can see the paper for further details about that. Since I'm running short on time, I'm going to skip this. We do have several optimizations for the specific application of our protocol to the MPC-in-the-head paradigm, but you can see the paper for that. So what I've described, you can run in a 5-round protocol. And if you're OK with interaction and if you're OK with honest verifier zero knowledge, then that 5-round protocol can just be used. It's also possible to make that protocol non-interactive because fiat shamir actually can be applied to any constant round protocol, but the concrete security of doing that would suffer. We can compress our protocol actually to a 3-round protocol where we get roughly the same communication with a slight increase in the prover computation. For doing that, I'll refer you to the paper for further details about that as well. I'll mention this just quickly because I think it's something interesting that was missed in prior work. Even when we apply fiat shamir to a 3-round protocol, you may be familiar with the fact that the concrete security reduction that you get from fiat shamir is relatively weak due to the use of the forking lemma. But we can actually do better and get a tighter reduction by specifically exploiting the fact that we work in the random oracle model. So we achieve proof size linear in the size of the circuit. We have the same, therefore, asymptotic communication complexity as ZKBoo and ZKB++, but we have better constant factors. We do have worse asymptotic communication than Ligero, but as I'll show in the next slide, we're still better in terms of communication for a certain range of what I'll call medium-size circuits. And we also have, at least at the time of submission, asymptotically better prover computation. So this is basically the kind of takeaway point here. So this is comparing the proof size for ZKB++, which supersedes ZKBoo. And the solid lines are our protocol taking n equals 16 or n equals 64. And one thing to see is that our protocol always outperforms, or at least above 100 gates or so, outperforms ZKB++. And it also outperforms Ligero, at least roughly in the range from about roughly 100 to 100,000 AND gates in the circuit. So it turns out actually, and this was a little bit surprising to me perhaps, but you can do a lot of interesting things with 100,000 gates. And in particular, that's enough gates to construct not only regular signature schemes using our NIZK proof, but also more complicated schemes like group and ring signatures. So we can apply our protocol in kind of a standard known way to get post-quantum signatures. Because our NIZK protocol is based entirely on symmetric-key primitives, there are no known quantum attacks, perhaps otherwise the possibility of a Grover-style attack, meaning that we have to increase our key sizes by a factor of 2. I will say with a caveat, though, that in the paper we only prove classical security based on quantum secure assumptions. We don't actually prove quantum security and don't consider access to a quantum signing oracle. I'm going to skip this because it's a little bit standard and I'm running a little short on time, although I think I have an extra minute because I started a minute late. Well, who's going to argue? So this is the end result for our application of our NIZK proof to signature schemes. I want to highlight 2 things. So first of all, I want to highlight the comparison to the signature scheme constructed using the same ideas in the ZKB++ paper. You can see that our signature size all the way in the column on the left is about 2.5 times smaller than their scheme. And the computation for signing and verifying in our scheme is slightly larger, but not significantly so. Another thing to look at is to compare what we can achieve in our paper to a construction of signatures based on a Merkle tree style approach called Sphinx. And here also we're actually able to beat the signature size of their published construction, although here our signing and verification times are significantly worse than what they can achieve. And we are working with the Picnic team. So this is basically a submission to the NIST post-quantum standardization effort that was done by the ZKB++ team. And we're working with them actually to incorporate our improvements into their submission and to have that ready as a revision to the NIST standardization process. So this is my last slide, and then just I'll end. So as I said, we can construct post-quantum ring and group signatures as well. To the best of our knowledge, these are the most efficient such signatures with post-quantum security. I'll refer you to the paper for details. And let me just say this, what I find really cool about this line of work is that it's theoretical insights beginning from the MPC-in-the-head paper 10 plus years ago, leading to practical constructions. And here we've just shown that we can extend and optimize this MPC-in-the-head approach to get shorter NIZK proofs and competitive post-quantum signatures. And I think there's still room to play in further optimizing and pushing these ideas. And so I look forward to seeing that develop. So thank you very much.
You mentioned that you get a tighter reduction for the Fiat-Shamir. Can you?
Oh, so it's not for Fiat-Shamir in general, it's for our particular protocol.
Okay, can you elaborate?
Yeah, so basically, just imagine at a high level, you have a 3-round public coin protocol, and the first round is a bunch of commitments. And because the commitments are done using the random oracle, you can extract directly from those hash queries.
Okay, thanks.
So I have more slides. I can keep going.
Since you have time.
Just ran out.
Oh, well. Why the preprocessing? You don't have the same property that that you will be able to see two parties being inconsistent? Is the preprocessing the usual thing?
Okay. So it depends on the preprocessing. You can imagine that there are preprocessings where you can locally check, but in the preprocessing we use, there's some property that you can only check if you have all n.
So you're not using the multiplication triples, for example.
We're not using multiplication triples,
Okay.
right? But even if you did, depending how you implemented that, if you had the multiplication triples additively shared in n out of n fashion, you wouldn't be able to check unless you opened all n.
But don't you have the...
Right.
We can talk about it later. But whatever you're doing in the online phase, wouldn't that be somehow the same in the offline phase? That's what I'm trying to...
So again, actually, the multiplication triple is a good example. So there you would give n out of n additive shares of a, b, and c, with a, b equals c. And unless if you open any n-1 parties, you just get random stuff and you can't check it.
Thanks.
Let me tell you about another result. So, yeah. All right.